In this video, we're going to take a look at putting together a Tally controller for the Spyder video processor. At the end of the video, we'll have a device that'll toggle relays on and off based on specific sources going on and coming off screen. We'll get started by setting up the hardware, and then we're going to write an application that'll listen to Spyder traffic and manage our tallies. So let's get started by taking a look at the hardware platform we're going to work with. Over the last year, there's been a ton of new, small, cheap, and general purpose hardware devices out there. So we have a lot of different off-the-shelf solutions that we could tackle the project with. I've decided we're going to use the Raspberry Pi 2 hardware platform. So let's take a second look at this little board. For 35 bucks, the Raspberry Pi 2 is a really cool offering that has a quad-core 900 megahertz processor, a gig of RAM, a 100 megabit Ethernet connection, a ton of I/O interfaces, and supports running a few variations of Linux, and even an embedded version of Windows 10 that Microsoft launched roughly at the end of April 2015. You can pick it up as an individual board for 35 bucks, and you can get it on Amazon, Element 14, a couple other sites. But I picked up mine as a kit from Amazon, which I would definitely recommend. It goes a little closer to 70 bucks, but for that you get a Wi-Fi adapter, an SD card that'll hold the operating system, a power adapter, a heatsink, and a couple other goodies. So we're going to take our Raspberry Pi board, and we're going to connect it up to a Tally/relay board. So the one that I have is a 8-channel relay that I picked up on Amazon for about 9 bucks. This little board has 8 input lines to control whether each one of the Tally contacts are open and closed, so it'll be pretty easy to hook up to our Raspberry Pi. The Pi itself has a 40-pin header that exposes all of its I/O options, and I've picked 8 general-purpose input-output pins for these relays. We're also going to have to pull over a 5-volt line and a ground wire to power the relay board. Once these two boards are hooked up together, we'll effectively have our final hardware platform, and then we'll just need the software. There's one last little bit. So as a test harness for this project, I made a little breadboard with 8 LEDs, which will serve as kind of a Tally light simulator. It'll help us with debugging and allow us to see our Tally controller actually working. So real quick, let's take a look at what the hardware looks like once we have these pieces hooked together. So here's our hardware setup. We've got a Raspberry Pi 2. We're connected in over Ethernet. Here's the 40-pin header off that, of which we're using 8 GPIO wires, which are coming over into our 8-channel relay board. So we have 8 GPIO, and then there's a 5-volt connection and a ground. Then on the other side, where our tallies would hook up, we're running out to a breadboard that has 8 LEDs, which we'll use for testing our relay to make sure it actually works. And these guys are being powered just off of a simple 9-volt battery setup. And that's about it. So now that we've taken a look at the hardware, let's turn our focus onto the software portion of the project. As a primer, we're going to spend a minute talking about a couple aspects of how your Spyder is working under the covers and how we'll be able to leverage its architecture in our project. Then we'll spend a minute discussing the OS and the application platform, and then finally we're going to dive into some code. So the Spyder server talks a number of different protocols, and those protocols vary depending on who the client application is. So in the case of something like Vista Advanced, most of the control happens over a .NET remoting protocol. So it's very proprietary between Spyder and Vista Advanced. External applications, including the Spyder client, talk using the publicly available external control API. Those protocols are basically point-to-point. The client application makes a request to the Spyder server sends back a response. And that's fine. One of the protocols that it also talks, and the one that's going to be really interesting for our Tally project, is a live data stream that we refer to as drawing data. Drawing data is a compressed byte-packed stream that contains all kinds of real-time status information about the server, including layer keyframes, outputs, router assignments, some pixel space information. All of that gets transmitted in this multicast stream. So the Spyder server can send it out one time, and it can be consumed by n number of clients out there. So this last point's important. The use of multicast traffic to serve multiple clients simultaneously means that the Spyder server can serve a large number of clients without incurring additional overhead with each client. Effectively, the Spyder server doesn't care if it has 0, 1, or 100 clients connected at any time. To be a good Spyder citizen, our Tally controller is going to listen to those same broadcast and multicast messages coming from the Spyder server, effectively leaving the Spyder unaware that our Tally controller is on the network at all. And not to really beat on the point, but let's talk for a second about how we're not implementing our Tally controller. An alternate way of building the software would be to leverage Spyder's external control protocol and pull for layer status information we need to determine which sources are visible in program pixel spaces. The code would basically put us into a tight loop where we query for layer keyframe and source information one layer at a time, as fast as we could, and we'd use up a decent amount of network bandwidth and Spyder processing power to do that. On a larger system with something like 32 layers or more, it could take a while to get through that full loop. So even best case scenario, our Tally switching might appear sluggish or delayed. Now for most implementations, the polling route's probably the way to go anyway. Deserializing that drawing data message on the network is really hard, especially since it's not publicly documented. So without leveraging an existing library to handle this for us, the project would be exponentially more complicated. Luckily, we are going to leverage an open source Spyder library that's written for .NET Desktop and store applications. So to leverage that Spyder client library, we're going to be running the Windows 10 IoT Core as the OS on our Raspberry Pi 2. So this edition of Windows, and it's essentially a compact, stripped-down version of the Windows OS. So missing from this is any kind of desktop, user interface, and most of the service GAC that's needed for the OS on a full desktop. It's designed to run embedded style applications, and by using it, we're going to be able to still use our Windows platform libraries that were originally written for Windows 8. So here's basically the full software stack. We're going to be running Windows 10 IoT Core as our operating system. We're going to be writing our Tally controller as a universal Windows application. Our application is going to leverage two libraries. The first is the Windows IoT Extension SDK, which is going to give us access to the GPIO ports on the Raspberry Pi. And then we're going to pull in the Spyder client library from NuGet to handle our Spyder communication. And the application that we're going to write here in a second is going to look something like this. Basically, when our application starts at boot of our Raspberry Pi, we're going to initialize our 8 GPIO pins as outputs, and then we'll set them to off. Then we're going to initialize a class called Spyder Client Manager, and then subscribe to an event that'll let us know when spiders are detected on the network. When our target Spyder server is actually detected, we're going to subscribe to an event on it, which will give us a real-time data feed for that server. That's a drawing data packet that contains all of the live status information that we care about. Then in the handler for our real-time drawing data, we're going to loop through the layers and figure out which sources are sitting in program and visible, and then turn on the corresponding GPIO pins. Every time we get the drawing data packet, we'll reevaluate which tallies should be turned on, and we'll turn on and off as necessary. So now that we've kind of talked through everything, let's actually put it together and make something work. So now we're going to go fire up an instance of Visual Studio 2015. If you don't have Visual Studio, they have a free community edition that lets you do pretty much everything that you would care about up until you start getting into like enterprise software development. So everything we're doing here, you could definitely do on the community edition. So let's just go and create a new project real quick. We're going to create a universal blank application, and let's go put it in ctemp. We're going to call it Spyder Tally Controller, and okay, so now we have our universal application. At this point, it's just a stock Windows application that can be used to deploy desktop or laptop or phone or Xbox or a little Raspberry Pi. There's nothing really special about it yet. So little bit of housekeeping we have to do first. We need to go into this package Apex manifest, and we need to declare that we are going to use a couple of capabilities. Capabilities are a security mechanism that they introduced back in Windows 8 store apps, where you basically have to tell it, hey, I want to be able to, in this case, access local area networks and possibly internet connected networks. Without that, any kind of socket stuff we do, like if we want to start listening to Spyder server streams, that's going to fail. So we just have to kind of put that in. So we'll save that, and then we're going to just go right into our main page. In this page, we'll put all of our code. It should be a really short application, and initially we're going to create this headless. So the Raspberry Pi does have an HDMI output on it, and so we could actually make a UI that would show up if you had a monitor connected. For what we're going to build initially, we're not going to do anything with the UI at all. So let's go and pull in our libraries that we need first. So the very first one we're going to need is going to be that Windows IoT extension, and we go into extensions and find Windows IoT extension SDK. So that's going to give us access to our GPIO. Then we need to go and pull in our NuGet package. So NuGet is an online library repository where people can publish their libraries for other people to consume. It's super handy. And luckily enough, there's a Spyder client that lives out there. So Spyder client library, it's at 101. We'll say install, and it's going to tell us that it's going to pull in PCL storage. It's a storage library that works across the desktop, phone, and the store type apps. So we don't necessarily care for our app, but it's going to pull in that extra reference. Okay, looks like it's done. Let's go back into our main page here. And the first thing we're going to do is we're going to hook to an event called loaded. Now, loaded happens when the page is actually loaded. And that's where we're going to put our initialization code. The biggest reason I'm not putting it directly in the constructor is because I need to be able to await certain things. This is a concept I'm not going to go over right now, but you'll see me using another keyword that goes with async here in a second called await. So let's go and get our GPIO going. So we'll say, let's grab a controller instance. GPIO is going to be GPIO controller. And we'll pull in the namespace Windows devices GPIO. And on that class, we're going to call get default. So this is going to give us an instance to a GPIO controller for our Raspberry Pi. If we go and run this application on the desktop, because it's a universal application that's valid, you would end up just getting null. So now that we have a GPIO, we're going to grab the pin numbers and initialize a bunch of GPIO pins. So let's say and from our pinout diagram from earlier, we're going to say we're using pins 18, 27, 22, 23, 24, 5, 25, 5, and 6. Note that those aren't the pin numbers, they're the GPIO numbers, so it kind of tripped me up early on, but if you look at some of the pinout diagrams, you'll see it's GPIO 18, not pin 18. So it's kind of a minutia thing. Now we're going to say we want to hold an array of pins, and we're going to want to keep those outside of our method. So let's go add a private field called GPIO pin array. We'll just call that pins. So let's say pins, new GPIO pin array, and that's going to be of the length of of our pin numbers, which is basically going to be 8. But we'll make it real verbose. So then we'll say for okay, now we'll just step through our pins. And we'll say var pin equal to GPIO open pin. Add our GPIO pin number. We're going to set its value to low. And set drive mode. So now we've set it to low, but we actually need to tell if that's an output pin, because each one of these GPIO pins could be outputs or inputs. And then we'll put that pin in our collection. We'll say pins I is equal to pin. Okay. Now we need to initialize our Spyder client manager. So we're going to need to go and do a little bit of minutia here with this PCL storage concept, the disk storage. So we actually have to new up something called an I folder that lives in the PCL storage namespace. This folder, we'll just call it local cache. So we're going to create a folder inside of our application storage space called server. And then we'll say collision create option, open if it exists. So if it already exists, let's just open it up. You don't have to worry as much about that. It's kind of ugly details, but luckily there's not much of it. Then, let's see here, we're going to create a Spyder manager, or Spyder client manager, and I'm going to want to make that global also. So let's say Spyder client manager, and we're going to have to pull in the Spyder client namespace for that. And we'll just move that guy out. New Spyder client manager, and here it wants our local cache folder. Now we're going to hook to an event on here that lets us know when the serverless changes. I'll leave that alone. We'll come back to that in a second. And then we're going to say Spyder manager dot startup. So now in our Spyder serverless changed event, we want to say, we want to check and see if our Spyder has actually been initialized so far. Now we don't have one, so let's go and create a client instance, and he is going to be of type bindable Spyder client, and we have to pull in the spider.client.net namespace to make that a happy entry. Just call him Spyder. Server. We'll call him Spyder server. Okay, so now when we get our serverless changed event, we're going to say if our Spyder server is null, we haven't initialized it yet, let's try and get an instance to it. We'll say Spyder manager get server. Okay, so now it's going to say what server IP do you want? That's going to be the server IP address of the Spyder that we want to be listening to watch for source changes. In this first thing that we're going to make, we're going to hard code those. And in another video, we're going to come back and actually build a desktop UI that allows us to configure it remotely, because this is headless. So I'm going to steal a little block of code that I can put over here. So for this initial thing that we're playing with, we're going to hard code our Spyder IP address to 192.168.1.100, and then we're going to hard code the source tally list to this list of sources right here. And again, we'll come back later and make an application to make that configurable remotely. So for now, we can now set this to Spyder IP. So if that server exists, then it will no longer be null. So if we do a quick check and say if Spyder server is not equal to null, then you must have just gotten an instance to it, so it must be on the network now. So we'll say Spyder server.drawing data receive. And now we're hooked to an event, which is going to give us that real-time status data we were looking for before. So here's where the meat of our tally controller logic is going to live. Basically, we're going to get called into this event handler every single time we get a status update packet from the server, and we're going to go through and find the list of sources that are currently visible on program, and then we'll update our tallies from that list. So let's start out by grabbing an instance and drawing data off of our arguments. Drawing data. And then let's build a map of sources. We'll say we'll do some old school link. We'll say from. So from all of our drawing keyframes, we're going to join those to the parent pixel spaces. Which, handily enough, is also in drawing data. And we'll link them by saying layer.pixelspace_id equals pixel space. Let's change it to pixel space. ID. And I'll say where layer is visible and pixel space scale is 1. 1 is a magic number in Spyder, so if it's a program pixel space, then it'll be exactly 1 for its scale ratio. Even in cases where a preview pixel space is the same size as program, we actually play some games to make sure that it's actually slightly less than 1. And so it's a cheat way to know if it's a program or a preview pixel space. There's a couple other ways we could look up linking tables, but we're going to cheat and do that. So we'll say let's select layer.source, and then since it's on multiple layers, we'll say distinct. And then we'll dump it out to in the list immediately. So now, with this little block, we will have the list of source names that are currently visible in program. Now for the fun part, we'll go and update our tallies. So this part's really pretty easy. So we're going to say, we're going to go and update each one of our pins. We'll say if let's make sure we'll do a quick sanity check on our bounds for our source tally list. And basically if we've written off the array, then we'll say oops, inside right below. So let's say string source okay, so we're going to get our source that represents that tally at this index, and then we'll go and do a compare. So if basically, hey, if this guy is in our list of sources in program, then we need to show it. We'll say pins right high value to turn on our tally. Otherwise, make sure that it gets set low. And that is basically the entire application. So we find our list of sources in program, and for any of our tally source indexes that are actually in program, we're going to turn on the light. Otherwise, we're going to turn them off. That's it. So let's build it, make sure we don't have any errors. Cool. Okay. Now, to push it over to the Raspberry Pi, we need to switch the configuration to ARM because it's an ARM processor that's running on there. And we'll switch it over to a remote machine. So we're going to connect to this remote machine, and we need to know its IP address. Now, if we had a monitor hooked up, it'd be really easy because it's going to be right on the screen of the monitor. But since we don't, there's a handy little tool called the Windows IoT Core Watcher. This comes with the SDK, and it listens on the network for messages identifying these Raspberry Pis. So here's mine. He's at 192.168.1.144. And he can authenticate with no auth. And now let's try and run our app. So it's built in ARM. It looks like it's copying 17 megabytes over to the device over the network. And hopefully in a second here, we'll start running. Cool. It looks like we're starting to debug. It's loading up some DLLs for debug. And there we go. I don't know if you can actually hear that, but our relay is just all clacked off. And now, because we're in Visual Studio and we're debugging, we can go ahead and do fancy things like set a breakpoint. Now it's hit our breakpoint, and we can step this code that's executing over on our Raspberry Pi. So let's take a look at this. Looks like we have 3 sources up in program. So we have something with no source, then we got camera 2 and PC2. So, just for sanity, let's go pull over our Spyder client. Camera 2 and PC2 up in program. So very cool. Okay, so let's get that out of the way. And we'll kind of walk through, we'll just walk through one iteration of this real quick. So we're doing a check for our source. Our source is PC1, which is not currently on screen. So we make sure that that relay stays low. And our next source should be PC2. We just saw it is on screen, so it's going to be in that list, and so that relay will be high. So now, if I go and remove one of these sources, then, I don't know if you can hear the click again, but now our list has changed. And if we go back and set one more breakpoint, we should see that PC2 is no longer in program. And we do. So cool. It looks like our app works. So let's go back and review. So I'm running Vista Advanced down here, and I've configured the Pi to basically follow the source numbers to the relays. So PC1 is going to be on tally relay 1, PC2 will be on 2, DDR3 will be on 3, and so on and so forth. I've also got that Spyder client running up here, and I'm going to use this to kind of show because it's bigger and I think it'll translate a little better onto my little screen here. So let's go and pop out our content bar and start dragging on some sources and kind of watch what that looks like. So if I take PC1 and I bring it on screen, then we'll see tally 1 come on because it's mapped. If I go and take that layer now and transition him off screen, as soon as he becomes completely off program, so notice it didn't happen immediately, that's when it's going to turn the tally off. So if I go in the reverse way, it should immediately turn on the tally because it's going to hit program while it's fading in. and you can kind of hear the click. And then if we transition it one more time, we hear the click once it's faded completely out. So if we go and drag on a couple more sources, we'll put this layer over here, we'll put this guy over here, and over here, then we'll see a few of these little tallies popped on, and you can imagine the rest of them would work if I keep dragging on sources. Just to show I'm not cheating, same thing's going to work from over here. So if I take this to advanced, transition that layer, you hear it click, transition it back, right? Same thing will work with command keys, so it's watching the same kind of state. So we've got camera 2 and PC 2, so that's going to be relays 2 and 4. And if we look over here, relays 2 and 4 are on. So let's finish this up with a quick summary. Throughout this video, we connected a relay board to a Raspberry Pi 2 running Windows 10 IoT Core, wrote a Windows Universal app to switch the relays based on Spyder sources on screen, and finally we deployed that app and got to see it running. So now we have our controller technically working, but we've left it hard-coded with the Spyder server address and the source names being used to control the tallies. In the next video, we'll clean that up by adding a desktop app that'll configure the tally controller remotely. Till then, I really hope you enjoyed watching the video, and thanks for watching.